Hello, I am Bharath. In this presentation, we'll be discussing on Gaussian process occupancy maps. Before moving into the presentation, it is important to know what an occupancy grid is. Occupancy map is a problem of generating maps from sensor measurement. The map is basically represented as a grid with discrete cells. Each cell represents whether the cell is occupied or unoccupied. Uh, like we can also represent the cell as gray in case of uncertainty. Occupancy grid has been in wide use for a long time due to its less computation requirement and simplicity. However, there are some obvious drawbacks for occupancy grid. Occupancy grid assumes that individual cells are independent of each other. It assumes that there is no spatial dependency in the occupancy grid. But however, in reality, the context of structure of the environment provides more information on the occupancy of the cell. Uh, Suppose, let's say, if there is a cell in the middle which is represented as occupied, it is logical to think that the neighboring cell is also occupied, since like an obstacle has a structure and uh, like it won't just be a single cell. So these assumptions usually result in cells with high uncertainty and is usually misclassified. The occupancy grid also suffers with discretization errors since the representation is discrete. Let's also look into what a Gaussian process is before diving into the crux of the paper. A Gaussian process fits a function to the input data. It determines the mean and variance of each random variable, uh, also known as cells in our case. Uh, in the image, we can observe that multiple observations are fitted into a function with mean and variance at every random variable. Here, the random variable is the x-axis of the graph. Uh, there are numerous applications to Gaussian process. It can be used to solve classification and regression problems. It can learn behavior characteristics of nonlinear and non-parametric functions. It can model noisy, sparse, and real-world phenomena. Gaussian process can fit a likelihood function to the training data. In this case, training data is the 2D map of the environment, and the likelihood function is the likelihood of the occupancy in the grid cells. This paper presents a few ideas to overcome the drawbacks of occupancy grids. Firstly, it introduces dependencies between neighboring cells using a Gaussian process approximation strategy. Uh, an accurate map, even in the case of noisy and sparse data, is generated. A continuous representation of map with mean and variance is calculated. The continuous representation can be leveraged to represent the unexplored area. So this is the outline of the Gaussian process-based occupancy map. Initially, the sensor data is collected from the real-world environment. The sensor data is processed into occupancy points. These points are stored in a KD tree like data structure. This will be referred as training data from now. The training data can also be from a simulation environment. A Gaussian process is trained with a set of hyperparameters to fit the discrete occupancy points and transform it to a continuous representation. This continuous function is represented as mean and variance at each occupancy point. The continuous function is further passed through a classifier like least square classification algorithm to predict the occupancy cells. Let's also look into how Gaussian processes are represented. Here, f of x is the Gaussian function that the map is going to be represented as. X is the input training data, which is basically the occupancy points. Mu and sigma are the mean and standard deviation of the occupancy process map. K is the covariance evaluated at all pairings of the input data. Y is the noisy observation of the sensor. X star is the location where we want to know the state of, and sigma n is the noise of the overall map. So the paper proposes two algorithms to generate Gaussian process occupancy maps. One takes into account the noise of the input and the other one doesn't. We'll look into the algorithm that considers input as precise measurements for now, which is basically it assumes that all locations are fully observable. Uh, the input to the algorithm includes the range and bearing observation from the laser sensor and the localization of the vehicle. The hyperparameters are set appropriately. The observations are mapped into then after the hyperparameters are set, the observations are mapped into Cartesian coordinates and the occupied cells are determined. The free cells are determined from the occupied cells using the sensor model equation. The covariance of the sensor measurement and the localization are calculated from the covariance function of the Gaussian process. The found covariance can be used to calculate mean and variance of the observation. Unlike the previous algorithm, Gaussian process assuming partially observable locations takes into account the noise in the sensor observation and the localization. The algorithm is almost similar to Gaussian process, assuming the locations are fully observable. The input takes covariance of observation and localization additional to the inputs in the previous algorithm. The posterior mean and covariance of the occupied and unoccupied regions are calculated from these covariances and other input, and the collective predictive mean and covariance is calculated from the posterior mean and covariance. This determines the likelihood of the occupancy in a map given the information of noisy measurements. So this is basically the comparison on Gaussian process assuming noisy and noiseless inputs. We can observe the mean of the Gaussian process assuming noiseless input deviates far from the ground truth when the noise is introduced to the input. The picture in the left represents the Gaussian process assuming represents the graph for Gaussian process when the input is noisy. Initially noise is introduced to the input and we can see there is a huge amount of deviation from the ground truth. However, as eventually the mean converges to the ground truth when the noise is comparatively less. On the other hand, in the right side there is no such introduction of noise to the input data, so we can see that the mean of the predicted Gaussian occupancy map doesn't diverge much from the ground truth. Here the top left image shows the ground truth of the environment. The vehicle is made to explore the environment and the sensor data is collected. The laser hits on the obstacle can be seen in the second picture. The third picture shows the output of occupancy grid. The boundaries of the map are not continuous, pertaining to the discreteness of the laser hits. The fourth picture shows the output of Gaussian process occupancy map. We can observe the map is continuous and the blue region represents free space and the red region represents occupied space. We can also observe the cells behind the walls are represented in yellow, establishing the uncertainty in those regions. The fifth image is the output of threshold filter. The threshold can be tuned as per the requirement. The final image depicts the variance of the output of Gaussian process. The variance is little higher in the corridor where sparse measurements are observed. In this experiment, two vehicles are made to explore the environment to collect sensor data. Platform 1 collects accurate sensor data and moves slowly in the left part of the environment. whereas platform 2 collects noisy sensor data and moves quickly in the right part of the environment. The red cells in the map represents the occupancy region and the blue cells represents free cells. Other color represent uncertain states. The leftmost image is the output of occupancy grid. We can observe that the obstacle are detected only at the laser hits and nearby cells are considered as uncertain states. Opposed to this, the middle image represents Gaussian process assuming fully observable location. The nearby cells in this case are determined as obstacles due to the continuous representation. However, there are still many misclassifications in the border of the obstacles. We can see the algorithm outputs an unstructured border, very different from the ground truth. The third image is the output from the Gaussian process assuming partially observable locations. The boundary is very smooth in this case. The right side of the environment where only sparse measurements are available made the boundary a little uncertain, but the free cells are accurate and are in line with the ground truth. This is the ROC plot with true positive in the y-axis and false positive in the x-axis. An ideal classifier should be located at 0, 1, which is top left corner of the ROC graph. Occupants in the right we can see the occupancy grid versus Gaussian process occupancy map. The Gaussian process occupancy map is performing relatively well compared to occupancy grid. We can see that the Gaussian process occupancy map produces a tube positive rate of more than 90% for a very insignificant false positive rate, whereas occupancy grid reaches 90% of true positive rates only when the false positive rate reaches 20%. On the left, Gaussian process for partially observable locations performs relatively better compared to Gaussian process for fully observable locations. We reached the end of the presentation. We'll have a short brief on what this paper has achieved. The paper proposed a Gaussian process to achieve continuous representation of occupancy map. The continuous representation makes Gaussian process occupancy map an anytime algorithm. Local approximation of covariance matrix for noisy inputs reduces the computation time to a significantly lower value. Noisy data from multiple sensors with uncertain observations can be combined to provide an accurate occupancy map. The formulated Gaussian process for the paper formulated Gaussian process for partially observable locations. This made the variance no longer depend on hyperparameter or input data with ambiguity. Gaussian process learned dependency between neighboring cells, resulting in accurate inference of uploaded cells. Thank you. Any questions?